So now we get to strong induction. So we've been talking about induction so far. What is strong induction? Well, this is covered in the Book of Proof, section 10.2 and Rosen 5.2, but the whole basic idea behind it is as follows. In just plain normal induction, we had to prove in the induction step that P of k implies P of k plus 1. We had to do that with normal induction. But what happens if you run into a situation and it turns out to be really difficult to prove that P of k implies P of k plus 1? What happens if maybe it was easier if instead of showing P of k implies k plus 1, what if it was easier to show that P of k minus 1 implies P of k plus 1? Maybe because the algebra works out easier or something like that. Or maybe it's easier to show that P of k minus 14 implies P of k plus 1. Some other case like this. So we can't use normal induction here because we're not going from k to k plus 1, even though this might be easier to prove. So the difference between normal induction, which is looking at this kind of implication in its induction step, strong induction is going to allow us to use these previous steps in our induction step. So a proof by strong induction proceeds as follows. So a proof of strong induction, and notice that it's the same kind of statement that we're looking at for all natural numbers. Some propositional function is true. So the way that it proceeds is very similarly. We still have a base case. And it's the same exact base case. We have to show that P of 1 is true. We have to start somewhere. We start at the very first one. Side note, but important side note, some different flavors of strong induction will require you to show more base cases than just the first. And we'll see an example of that in a bit. Where strong induction differs than normal induction is in the induction step. So here, our induction step looks a little bit more complicated, but it actually will make our lives easier. How so? So for arbitrary k, we need to show that this big conjunctive statement here implies P of k plus 1. So the really nice thing about this is if we're using a direct proof technique, we get to assume all of these previous steps are true. P of 1 is true, P of 2 is true, and P of k is true. We get to assume all of those are true, and we try to show that that implies that P of k plus 1 is true. After we show this, we can then conclude that our statement is true. So the reason why it's really helpful in this induction step that our hypothesis is this big old conjunctive statement here is it allows us to access information about all the previous steps. So here when I said that it might be easier to show P of k minus 1 implies P P of k plus 1? Well, that's just this guy right here, the one step beforehand. P of k minus 14, that's somewhere back further in here, etc. So what strong induction does is it allows us to access all the information, assume all these past steps, and then try to show the very next step. So in our ladder analogy, we had our very first base case right here, P of 1. And then what standard induction did is it says if we are at one rung, like the kth rung over here, then we can get to the k plus first rung. And that's why in normal induction, we are going from P of k to P of k plus 1. If we're at one rung, we can get to the next one. So it's taking just a single hop over here. The way that strong induction differs is that we have assumed in our hypothesis right here that we have hit every single other rung up until the kth one, and then we just need to show the next step. So what it does is it assumes that we have been on this rung and this one and this one and this one and this one, etc., and then we just need to show the next step. So it assumes that we have already visited all these previous rungs, we can access all the information about them, and all we have to do is then show the P of k plus 1 right here. So that is the basic idea behind strong induction. It's called strong because you're assuming much more in your hypothesis than in our normal induction. In normal induction, you've only assumed that you're at the kth step. In strong induction, you assume that you have visited all the previous steps in your induction ladder as you try to prove your statement.